If x is approaching 2, the limit of our line is 1. So the indication of the dependent variable is counted also by the independent variable. Yes or no? As the independent variable is approaching a point, the dependent variable is also approaching its limit. Yes or no? Now, I believe you ask.
All right, guys. It's Oroluwa here again, and I want to use this video to quickly break down differentiability in its simplest form. Like, this video is meant to make this topic nothing to you. Do you understand? Because after yesterday's class, majority of you guys started complaining that the concept is quite confusing, and I guess it's because I was blending the idea of derivative and differentiability together, which looks quite confusing to some of you guys. Now, here's the thing. In part 1, you were taught differentiation, total differentiation. I mean, you have y to be equal to f of x in part 1, and then you were told that derivative of this guy is any f prime of x such that this guy's limit as a particular h tends to 0, a small value that is approaching 0, of the limit of the function of x plus h minus a function of x all over h. Yeah, this was what you guys were taught in part 1, and they called this first principle. Now, the idea of differentiability is not far-fetched from this idea, and we just have to build from here to make it much more sensible to you. Now, this is first principle. Do you understand? Now, the idea here is that it is actually possible for a function to be differentiable at a single point. Do you understand? So let's call the point x naught. Now, what happens if x is equal to x naught? That is, when do you see a function is differentiable at a point x naught like this? Now, if function f is differentiable at point x naught, if two things hold, which is the left-hand derivative and the right-hand derivative being or existing and both being equal. However, here's how you define differentiability at a point x naught. So you define it on x naught like this, f prime at x naught, which is equal to the limit as h tends to 0 of f at x naught plus h minus f at x naught all over h. We discussed all of this in class. Now, this is how you define the derivative at point x naught. Do you understand? Now, you should note this, which I observe most of you didn't really note, and that point is that if f prime at x naught exists, then keep this in mind. Then we say that the function is differentiable. Please follow through. We say that the function is differentiable. I repeat, if this particular condition or this definition exists, then we say that the function is differentiable at x naught. Or another way to write it or put it is that f has a derivative at x naught. F has a derivative at x naught. So most of you guys just like to accept this idea, and then you find this big to use that. Why we say it's differentiable? Why are we not saying it has a derivative at x naught? Well, the moment this exists, then you say that the guy is differentiable at that point. Do you understand? It's differentiable at that point. Now, let's also discuss the two conditions I talked about for you to consider or observe before you conclude that a function f of s or f at x naught or f of x generally has a derivative at x naught. And what are the two conditions? Is the idea of right and left hand limit. Right and left hand limit. Right and left hand derivative. This concept you were given in class, right and left hand derivative. And what was that? Right and left hand derivative. Let's start from the right. That's f prime at x naught plus being equal to limits as h tends to 0 from the right? H tending to 0 from the right of f at x naught plus h minus f at x naught all over h. This is the right hand derivative. Now for the left hand derivative, we denote that by f prime minus at x naught, and this guy is limits as h tends to 0 from the left of f at x naught plus h minus f at x naught all over h. So note these two things. Now the condition attached is that, of course, these two guys must exist. The two of them must exist. However, a function f of x, so let's keep notes there. A function f of x has a derivative. A function f of x has a derivative at x equal to x naught if and only if the left and the right hand derivative are equal. If and only if the left and the right hand derivative are equal, like this. So now see, don't confuse yourself. You have a function f of x, and then they are saying confirm whether this guy is differentiable at a point x naught. How do you confirm that? Simple as ABC. You pick the function and then you evaluate the limit as h is tending to 0 from the left of this particular definition. Then when you're done doing that, you also evaluate the limits as h is tending to 0 from the right plus of, so you get f of what we have there, blah blah blah. Now you want to firstly confirm if these two guys exist. Then after confirming that, you also want to confirm if they are equal. If they are not equal, it means that the function is not differentiable at that point. Or what are you talking about? Example, if I ask you, is the function f of x, which is the modulus of x, is this guy differentiable at x equal to x naught? Before this concept, or before we start talking about the idea of differentiability, I'm sure you must have been thinking, what do they mean by is it differentiable at x equal to 0? Should be just differentiation. Why can't you just differentiate it directly and then just write the answer? No, they want you to investigate whether this guy is differentiable at this point, which means that you have to be critical with the idea. And how do you confirm if this guy is differentiable at this point? Simple. You evaluate the left hand and the right hand derivative, and you show them if they are equal or not. Good news, I'm going to be solving this question in this video. However, before I go into the question, let's consider the definition of differentiability itself. So everything I've discussed so far is just derivative. What you did in part 1, derivative. So, and don't also forget, I established here that if f prime at x naught exists, then we say that the function is differentiable. So you have the right to say the function is differentiable at x equal to 0. Like, don't be scared to make the statement differentiable even when you are solving at a point. Do you understand? Now, I told you in class, don't forget, derivative deals with a point. Differentiability is talking about an open interval, and I explained the entire idea of open interval, which is open neighborhood. But let's talk about it. Differentiability. Now, a function f is differentiable on a closed interval a comma b if it is differentiable in an open interval, and if the following limits exist. And what are the limits? This particular limit. Now, this is limit as h is tending to 0 plus. Now, it means that h at this particular point, a is here, you have an open interval, and b is here like this. This is an interval. Now, anything you have in this interval is approaching a from the right. So it means that whatever you have approaching a is surely greater than a, and anything in this interval is approaching b from the left of b. So which means that it is less than b. That's the idea, my friend. That's the idea, simple as ABC. And that is why it is limit as h tends to 0 plus of the function of a plus h. Now, we are saying that a function is differentiable in a closed interval if it is differentiable in an open interval, to just show you how critical differentiability deals with open neighborhood. Values approaching, and not the boundary point. Values approaching, not the boundary point. So values approaching a and b, and not the values of a and b themselves. So we are saying, x is approaching a from the right, and it is approaching b from the left. So how do you confirm differentiability in an interval? Good. All you just need to confirm is the limits as h is tending to 0 from the right. That is values approaching a from the right, and you have this definition, and then values approaching b from the left, these limits too. So if these two guys exist, then you say that the function is differentiable in that interval. Hence, we say a function is differentiable in a closed interval if it is differentiable on an open interval a comma b like this, and its right hand derivative and left hand derivative exists at a and b respectively. Simple as ABC. So it means that when you are talking about derivative is just a point. Where is a function differentiable, or does it have a derivative at this point? How do you confirm if a function has a derivative at the point? You confirm the left hand derivative, and then you confirm the right hand derivative. If the two of them exist and they are equal, then that means that the function has a derivative at that point. But differentiability is talking about open interval. So what do you need to check? You need to check what is happening with the limits approaching a from the right, limit of values approaching a from the right, and then what is happening when the values are approaching b from the left. If you confirm that those limits exist, then you are saying the function is differentiable in that interval. Let's solve some questions to deepen your knowledge. Now, this question says, investigate the continuity and differentiability of f of x, which is the modulus of x, at x equal to 0. So let's quickly solve that because of our time. This video is already entering 40 minutes. Now, in order to investigate the continuity of this particular function, it will be very much bright if we can define it out explicitly. Now, modulus function, we've defined that as many times as possible in class. The modulus of x is defined on positive x if x is greater than 0. It is defined on 0 if x is equal to 0, right? And it is defined as negative x if x is less than 0. Now, there are two ways to actually show this guy. If you want to be sharp and smart, you can just find the derivative of this guy directly from here. And of course, that's plus 1 if x is greater than 0. That's 0 if x is equal to 0. And that's negative 1 if x is less than 0. Now, if you check the 2 points, this is obviously derivative at a point, right? So if you check point 0, which is the only point we have, I told you derivative gives the point. you talk about differentiability as a whole when you're dealing with an interval. However, if it has a derivative at that point, then you see that it is differentiable at that point. Do you understand? Now, if you check what is happening when x is approaching 0 from the left, that is when x is less than 0, and you check what is happening when x is approaching 0 from the right, that is when x is greater than 0, from our definition, the value of the limit of this function as x is approaching 0 from the right is +1, and as x is approaching 0 from the left, we have -1, which tells you that the left hand limit at point 0 and the right hand limits are not equal. They are not equal. So that tells you just one thing, and that's the fact that this particular function does not have a derivative at point x equal to 0. Or another way to put it is that it is not differentiable at x equal to 0. However, if I ask you, is it continuous? Of course, there are 3 cases to check for continuity. Number 1, you check for existence of limits. Number 2, you check if the function is defined at that point. And number 3, you check if the first and the second condition are equal. So if you check for the limits, as x tends to 0 minus of the modulus of x, of course, that's the same thing as finding the limit as x tends to 0 of minus x, which is 0, right? Also, if you find the limit as x tends to 0 from the right of the modulus of x, you are finding the limit as x is tending to 0 of x itself, and that's also 0. So the two values are equal, they exist and they are equal. So that means that the limit of this particular function does exist at 0. The second case, or the second condition to check, is if the function is defined at point 0, and of course f of 0 is also 0. The modulus of 0 is 0, so the limit exists, the function is defined, and limits and the function at point 0 are equal, which implies that this particular function is actually continuous at point x equal to 0. So that tells you that it is possible for a function to be continuous and not be differentiable. Do you understand? So we see continuity does not imply differentiability. However, if it is differentiable, then it is surely continuous. So that tells you that differentiability implies continuity. I gave you that theorem in class. Differentiability implies continuity. The converse is not true. The converse is not true. Do you understand? Differentiability implies continuity. In case you are hearing my voice and you are not my student, well, you are missing, bro. Just join us. No stress. Join us for well-detailed explanation to concept. Now, the way I solve this question is quite, will I say, fast. Let's go through the route I taught you. I gave you some limit formulas. So let's use those limits ideas to solve this question. So from the left, we want to see if the guy is differentiable at point 0. So the limit as h is tending to 0 from the left of f prime of x, like this, which is same thing as the limit as h tends to 0 minus of f at 0 plus h, because this point is 0. Do you understand? At point 0, so then minus f at 0 all over h. That's the same thing as the limit as h is tending to 0 from the left of now if f of x is modulus of x, then it means that f at h from the left will be minus h, then minus 0 all over h. At the end of the day, you get -1 there, right? That's -1. And if you find what is happening from the right, limit as h tends to 0 from the right of the derivative, that's limit as h tends to 0 plus of f of 0 plus h minus f at 0 all over h. Now from the right, f of h is h itself, so this is h minus 0 all over h, which is plus 1. And you agree with me that the two of them just exist, yes, but they are not equal. And the condition for a function to have a derivative at a point is that the right and the left hand derivative must be equal. Don't forget, the right and the left hand derivative must be equal. Sorry, yeah, these two things, the two of them must be equal. The two of them must be equal. They must be equal. They must be equal. Don't let me, another way to express what I wrote there. Let me make it simpler for you. We should just write it as f prime at 0. This is from the left, and this is from the right. Simple as ABC. So, but the two of them are not equal in this case. I'm saying f prime minus at 0 is not giving us the same value as f prime plus at 0. So that means that the guy is not differentiable. Like, you don't need to stress. The guy does not have a derivative at 0, or better put, it is not differentiable at 0. Simple as ABC, my friend. Now, yeah, let's solve another question that looks like this, but a little advanced. They will now solve questions that has intervals so that it will make more sense to you. Alright, they want us to investigate the continuity and differentiability of this guy. Now listen very well. The initial function I gave you was defined as modulus. This guy deals with signs, so you know something is coming from the left and from the right. But this time around, we have critically x squared, which is a non-negative value. I'm sure you agree with me that x squared is non-negative. And then you have sine, which is a trig function. We all know that the sine of any x lies between +1 and -1, like this. So it means that all we just need to check as far as this particular function is concerned is if the limit as h is tending to 0 from of f of x naught, which is 0 plus h minus f at 0 all over h, if this guy exists, that's all. Look at the definition from here. I don't need it to get everything mixed up, just pay attention. Look at this definition I gave you. I said if this guy exists, then we see that the function is differentiable at x equal to x naught, or you get it, that's the derivative of. So we just need to check if this guy exists for that particular function. So whenever you need to be critical with signs, then the idea of left and right comes in, left and right derivative. Now, how do you check this? Simple, as I've already explained or defined. The derivative of this guy at point 0 is defined on limit as h tends to 0 of f at 0 plus h, like I defined. So that's f at h minus f at 0 all over h, which is the same thing as limit as h tends to 0 of now if you put h into this guy, the function at point when the guy is approaching 0, not when it is exactly 0. When it is exactly 0, you have 0. So that's why what we have here is h squared sine 1 over h then minus 0 all over 0. Do you understand? All over 0 all over 0. The only reason why this guy is 0 is because they give us in the definition. If they did not give us in the definition and we want to find f at 0, that will be the same thing as 0 squared sine 1 over 0, which is the same thing as 0 times infinity, and 0 times infinity is an indeterminate. So that's why they give us in the definition, so that we won't be hooked at that point. I just needed to chip that in. But yeah, let's go back. Now what we have here, sorry, it should be over h, not 0. Alright, now what we have here is then the same thing as limits as h tends to 0 of h sine 1 over h. Do you understand? Because this h will divide the h square here. Now the question is, what is the limit as h tends to 0 of h sine 1 over h? This is where squeeze theorem comes in, right? How do you do that? I mean, we know that sine 1 over h lies between 1 and negative 1 for any h. Do you understand? For any angle h. Now, with that said, if you multiply all through by h, you have minus h less or equal to h sine 1 over h, and this is less or equal to h. Now, if you evaluate the limit of both ends, which as h tends to 0 like this, if you evaluate the limit as h tends to 0 of minus h, you get 0, which is literally the same thing as what you get if you evaluate limit as h is tending to 0 of h itself. Do you understand? They are both zeros. So that means that this guy will give you 0. So it means that the derivative is 0. It exists, right? It exists. And because it exists, that tells us that this particular function is differentiable at x equal to 0. This particular question, they actually asked them last session. If this was not the question was very close to this. I will confirm. Check it. So this function is differentiable at x equal to 0. And of course, because it is differentiable, you can tell that it is continuous, very continuous, right? Why? Because differentiability implies continuity. The converse is not true. Do you understand? The converse is not the case. So let's solve a question that deals with interval. Do you understand? So that you understand differentiability well. Omo, I'm tired, but let's solve this question. This will be our last question for this video. Omo, the video is already entering 30 minutes. But I sure hope you are getting it. That's the most important thing. So they said we should discuss continuity and differentiability of this particular function, of course, in the intervals given. So I think we should start from the idea of continuity. And of course, continuity depends on the existence of limits. Now, at point x equal to 2, do you think this function is continuous? Let us check it together. Now, if x is approaching 2 from the left, of course, means that x is less than 2. Are you following? X is less than 2. Now, when do you think x will be less than 2 from what we have? So it means that if 2 is here, then x is approaching 2 like this. If it is from the right, it means that x is approaching 2 like this. From the right, it means that x is obviously greater than 2. Now, from what we have, it will be approaching x from the left. I'm saying x will be less than 2 or less or equal to 2. In this particular first function, you can see that for the first one, x lies between 0 and 2. So yeah, the limit as x is tending to 2 from the left of the function is the same thing as the limit as x tends to 2 from the left of 2x minus 3, which is the same thing. If you put 2 inside, you have 4 minus 3, and that is 1. If you check what is happening from the right, limit as x tends to 2 from the right of the function, of course, that's the same thing as finding the limit as x tends to 2 plus of x squared minus 3. Of course, like I said, that's when x is greater than 2. And from what you can see that x is obviously greater than 2. So if you put 2 inside, you have 4 minus 3, and that is 1. And of course, from what you can see, the limit does exist. Do you understand? The limit does exist. And if you put 2 into these functions directly, you will get defined values 1. And that tells us that the function is actually continuous. Do you understand? The function is continuous at this function is continuous, the function is continuous at x equal to 0. Sorry, at x equal to 2. Do you understand? The guy is continuous at x equal to 2. Now let's talk about the differentiability of the function, which is the main reason why we are here. Now, from what we were given, you can obviously see that we have intervals, closed interval of 0 and 4. I'm saying x is between this interval from 0 to 4. At first, it was splitted between 0 and 2, and then 2 and 4 like this. So if you check it very well, x is in this closed interval. So let's check the differentiability of x in this closed interval. Don't forget, from our definition of differentiability, we say that a function is differentiable on a closed interval if it is differentiable on the open interval. What's the idea behind the open interval? We said open neighborhood. Do you understand? So yeah, let's check it. The first thing we need to check is the existence of the left, that is this boundary, this boundary here, the limit from that end and then the limit from this end. Once the two of them exist, then we are sure that the function is differentiable in that interval. So I am saying the function from the right, of course, x is at the right of 0. Any x you have in this interval is at the right of 0. So I'm saying if this is the real line and this is 0 and 4 here, this guy is at the right of 0 and it is at the left of 4. So f prime at 0. Why? Because it is at the right of 0. Is equal to the limit as h tends to 0 plus or 0. You don't even need to, we've already indicated the sign there. Then of f at a, our a is 0 now. 0, you know, a is the boundary is denoted by a comma b, so that's 0 plus h minus f at 0 all over h. And if you evaluate that, as limit as h tends to 0, then over from the left, of course, that's 2x minus 3, so that will be 2h minus 3. Then minus, if you put 0 inside this thing, you get minus 3. Close that all over h, which will give you limits as h tends to 0 of 2h minus 3 plus 3. That means minus 3 and plus 3 will cancel themselves out all over h. H will cancel h, and the result here is 2. So we've seen that the right the right limit under differentiability, we'll come and see differentiability here. And we said that a function is differentiable if these two limits exist. That's a condition for differentiability, my friend. If these two limits exist, this condition here. So for this particular question, we've observed, or we've discovered that this guy exists. Well, let's check the other one, which is when it is coming from the left, when x is approaching 4 from the left. So we are saying f prime from the left of 4 is equal to the limit as h tends to 0. H must always tend to 0. Do you understand? As far as differentiability is concerned, of the function, then b is 4 now, so that will be 4 plus h minus f at 4 all over h, which is the same thing as the limit as h tends to 0 of, now from the left you have x squared minus 3. Do you understand? Why? Because x is less than 4 here in this region here, like this. X is less than 4 in this region, less or equal, and we are observing open interval, so x is less. So that means that what we have there is the same thing as 4 plus h all squared. I mean, what we have there is x squared minus 3, so that will be 4 plus h all squared minus 3 minus 3, then minus, if you drop 4 inside this thing, you will have 60 minus 3, which is 13. Then minus 13 all over h, which is the same thing as limits as h tends to 0 of if you open this thing up, you have 16 plus 8h, then plus h square minus 16, that's minus 3 minus 13 all over h. That's the same thing as this one will cancel this one out, so you have limits as h tends to 0 of 8h plus h square all over h. So h is common there. You have the limits as h is tending to 0 of 8 plus h. Do you understand? H will cancel the common h there. So if 0 enters, you have 8. Now we have discovered that the left hand derivative and the right hand derivative exists, and because the two of them exist, differentiability intervals, closed interval and then definition based on open interval is on existence of both the left and the right. Do you understand? So these two guys exist. One give us 2, the other give us 8. Because the two of them exist, we are sure that the function is differentiable. If it was at a point, then it means that the left and the right must give us the same answer. Do you understand? Which is derivative. But now we are dealing with boundaries, intervals, open intervals. So all you need is existence of the left and the right limits. Two limits. Once they exist, then you are sure that the function is differentiable in that interval. So that's it, my friend, and hopefully you understand this. There are still more questions to solve. I will solve them in the next class. Thank you so much. Do have a wonderful day.
And